Welcome to my class. I'm Drew Collop. In today's class, we're going to look at measurement and conversion factors. Honestly, this is probably the most important mathematics you'll learn in a first-year laboratory course. In the laboratory, converting between volume and mass and moles and mass are things you're going to do all the time. That is why I believe this is one of the most important lectures in a first-year laboratory course. When you talk about a number, this quantity only has meaning if there are units attached to it. If I was to say, I will pay you $4 to come clean my house, what does that $4 mean? It doesn't mean anything. There's no units attached to it. I will pay you $4 to come clean my house. That's not a very good deal. I will pay you 4 gold bars to come clean my house. That's a very good deal. Those units adjust what that quantity represents. As a result, when you're working in the laboratory, all numbers must have some sort of unit attached to it. Otherwise, it doesn't mean anything. There are a few numbers in the lab that do not have units. Things like logarithms and ratios, the units in here usually cancel out. When doing calculations, we require the units to be the same. As an example, if I say add 3 meters to 3 kilometers, the answer is not 3 plus 3 equals 6. Because those units are very different, I must convert them both to kilometers or both to meters. Therefore, you must have mutually consistent units. Oftentimes, it doesn't matter which one you choose, just pick one and convert them both to that. To make sure that scientists all over the world are speaking the same language, we work in SI units. This is a French system, Le Système International de Unité. This is the system of units that scientists have agreed to work in so that we are all speaking the same language. Most countries around the world have adopted these as their standard units. The main exception is the United States of America. Their scientists work in SI units, but the general population still works in pounds and in miles and units like that. These are non-SI units. As a result, it will be important to learn how to convert non-SI units over to SI units. That'll be the topic of another lecture. Let's review the rules for SI units. First of all, your decimal sign needs to be a point on the line. Quite often, students, they place the decimal point too high up, and this will represent a product multiplied by. So make sure when you're writing your decimal point, it's at the bottom on the line. The next rule is we do not use commas when grouping 3 place values together. When commonly writing numbers, this is done, and working financially in numbers, this is done. However, when working scientifically, we do not use commas. What we can use is a space between every third place value. That can happen here, as well as here. One of the main reasons we don't use commas in our SI units is because in some countries, a comma is used in place of a decimal. With this number, 16,543, does that mean 16,543, or does that mean 16,543? Again, what's very important is that we communicate in the same language. Next up, we leave a space between our number and our units. We do not write it like this. Also, if we have a decimal place that comes before any of the numbers, we do not write it like that. We always place a 0 in front of the decimal place. Throughout the course, I've tried to impress upon you the importance of these things for the reason that when you're working in SI units, this is the way. In addition to the rules with the SI unit system, units of measurement have also been defined. For these parameters, here's the units of measurement. For length, we work in meters, not in miles. For mass, we work in grams, not in pounds. For capacity or volume, we work in liters, not in ounces. For the amount of a substance, we work in moles. You'll be doing this a lot in your chemistry classes. The standard unit of time will be seconds. The standard unit for electrical current will be amperes or amps. The standard unit for temperature is Kelvin. Now here in Canada, when we measure temperature, commonly we work in degrees Celsius. In the United States of America, they commonly use degrees Fahrenheit. but neither of these are usually used in your calculations in the lab. We will work in Kelvin. Finally, the standard unit for luminous intensity is candela. Now, personally, I've never used this before, but I thought I would mention it. One thing to note, the definition of 1 milliliter is 1 centimeter cubed. These two things would be good to memorize, that 1 milliliter is 1 centimeter cubed. How I remember this is I think about it from terms of television. If you're watching one of those shows where it's dealing with an emergency room in a hospital, and the doctor yells out, "Give me 10 cc's of something stat." cc stands for cubic centimeters. What they're really saying, instead of saying 10 cc's, they're really saying 10 milliliters. But cc sounds cooler. So hopefully that will help you remember that 1 milliliter is 1 centimeter cubed, or 1 cc, centimeters cubed. Also note, grams is written as G. Please don't write it as GM. I see this often in students that are trained in other countries. They write grams as GM. This is incorrect. The standard unit of measurement of mass is grams, and it's just written as G. So please be aware of that. So we've talked about the standard unit rules. We've talked about the standard units of measurement. Now let's talk about the prefixes that come with the SI unit system. Here you can see the general standard unit for all of these measurements. The standard unit is going to be just 1, or 10 to the 0. By getting larger, 10 times, this is deca. Hecto is 100 times. 1,000 times is kilo. Mega is 1,000,000 times. Giga is 1,000,000,000. And tetra is 1,000,000,000,000. When getting smaller, 1/10 of the standard unit is deci. 1/100th of the standard unit is centi. 1/1000th of the standard unit is milli. Micro is 1/1,000,000. Nano, 1/1,000,000,000. Pico, 1/1,000,000,000,000. If you put these into practice with some of the common values you'll have to convert, we can add in our standard unit, and it changes things a bit. Here you can see for length. Our standard unit for length is meter, lowercase m. Commonly, when working with length, you'll work with kilometers, centimeters, millimeters, and micrometers, perhaps even nanometers. These small values you might work with in biology when you're measuring things inside the microscope. For mass, the standard unit is gram. Again, G is going to be the symbol. Units you'll work with is kilograms, milligrams, micrograms, and nanograms. Milligrams, micrograms, and grams will be very common in your measurements in the lab on the balances. Nanograms you might have to work with in your calculations. In terms of volume, the standard unit is liters. Symbol is capital L. Units you should know, milliliters, microliters, and nanoliters. You'll be measuring in milliliters and microliters quite a bit. Nanoliters, not so much, but perhaps you'll have to do some calculations for that. Finally, moles. Standard unit is MOL. Ones you should know, millimoles, micromoles, and nanomoles. Now you should be familiar with all of these values, but I would recommend those values I've highlighted that you memorize these. You understand what these represent. If you can do this, it'll improve your techniques in the lab greatly. Out of interest sake, I've looked up some larger prefixes and some smaller ones. Bring your attention to this one here. Google. This is actually where the website gets its name from. The website Google is actually spelled incorrectly. This is actually how you spell Google. And what Google represents is 10 to the exponent 100. This would be 1 followed by 100 zeros. Let's now talk about conversion factors. As I stated at the beginning of the lecture, this is a very important lecture. This is the most important concept when doing any calculations in a biology or chemistry lab. If you can't do basic calculations to make up solutions, you won't be able to work in the industry. So let's review how we use conversion factor method, also sometimes known as dimensional analysis, to convert from one unit to another. Let's pick something easy. How many meters are in 13.45 kilometers? So what we're looking to do is to take 13.45 kilometers and convert that into a certain number of meters. So how do we do that? Maybe you can do this in your head because this is an easy one. I've selected an easy one on purpose. Let's go through and show you how to do this using conversion factor method. Please note that I will only accept conversion factor method during my assessments when converting from one unit to another. You must show me all the steps. Let me show you something here. If I took my 13.45 kilometers and I multiplied that by 1, what do I get? 13.45 kilometers, right? If I multiply something by 1, its value does not change. So based on that, if I converted that 1 into 1 over 1, what is this equal to? Well, 1 over 1 is exactly the same as 1, right? Same number on the top and the bottom, so that's just worth 1. As a result, again, the value has not changed. What if I was to write this as times 4 over 4? What is this equal to? Now, because the value in the numerator is equal to the value in the denominator, again, this is equal to 1. As a result, the value of this does not change. So what I'm trying to show you here is as long as the value in your numerator is equal to the value in your denominator, this fraction here is equal to 1. As a result, it does not change the value of the number. So let's use that now to create a conversion factor. This fraction, moving forward, will be a conversion factor. What do I want now? I want to go from kilometers to meters. If I can find how those two things are equal, then I can solve this. Now, when I use conversion factors, I always pick the larger quantity and I make it equal to 1. So what's bigger, meters or kilometers? Well, kilometers is bigger. So 1 kilometer is going to have 10 to some exponent of meters. There's going to be a whole lot of meters in 1 kilometer. I use this method because this will always result in a positive exponent. It can be confusing to choose whether you put a positive or negative exponent in your conversion factor. As a result, I always pick a positive exponent. As long as you choose the bigger unit to be equal to 1, the smaller unit will be 10 to some positive exponent. Let's go to our chart and see what the difference is. So here I have kilometer and here I have meters. If there's 1 meter in a meter, this one here, 10 to the 3, there are 10 to the 3 meters in a kilometer. So we'll go back to this and I'll write in 1 kilometer is 10 to the positive 3 meters. So I've found two quantities that are equal to each other. So using the same rationale we had over here, let's write our conversion factor equation. 13.45 kilometers multiplied by. Now, what do I put on the bottom? I want to place on the bottom the unit I want to cancel out. I want to cancel out kilometers. As a result, I put kilometers on the bottom and meters on the top. I can invert this fraction, and it doesn't change the value at all. I have 1 kilometer is 10 to the 3 meters. You can see what happens here. Kilometers on the top, kilometers on the bottom. What I'm left with is meters. So here this gives me 13.45 times 10 to the 3 meters. If I want to write that in proper scientific notation, 1.345 times 10. This number is getting smaller, so this number gets bigger, 10 to the 4 meters. In standard notation, this would be 13,450 meters. This is the method I would like you to learn to convert from one unit to another. If you have another way of doing this, please put that aside and learn this method. It's very important you know this when you get into your chemistry classes. Let's look at the process of finding your conversion factor. Your conversion factor will be that fraction. What you need is you need the numerator and the denominator to be equal to the same thing. Up above, we said 1,000 meters, 10 to the 3 meters, is 1 kilometer. Those things are equal. If they are equal, the value does not change if the fraction is inverted. It also doesn't alter the number of significant digits. As an example from above, I could write this as 10 to the 3 meters over 1 kilometer, or I could write it as 1 kilometer over 10 to the 3 meters. The value does not change. What dictates whether you put 1 on the top or the bottom determines on which unit you're trying to cancel out. Because you have units on the top and the bottom, those can be canceled out if they're on opposite sides of your conversion factor. And anytime you can find 2 units that are equal, you can make this as a conversion factor. This will be important later on. Let's go through the process in example 2 at the same time. So example 2 asks us to convert from 4.6 microliters to liters. Step number 1, write down the quantity we are given. We're given 4.6 microliters. Notice micro looks like a U with a bit of an extra tail at the front. Next up, we want to multiply to get the correct conversion factor. I want to convert this from microliters to liters. Now there's an extra step here. It's an optional step. If I was going from microliters to kiloliters, the suggestion here is you go from microliters to liters first and then go from liters to kiloliters. We'll come back to that later on. Alternatively, you can just jump from microliters to kiloliters if you know the correct conversion factor. For here, liters is our standard unit, so we'll just skip number 2 right now. Let's look at our conversion factor. Again, I've placed microliters on the bottom because I have microliters here and I want to get rid of that. The next question is, what 2 numbers do I put in here? Well, remember, I picked the bigger unit. Liters is bigger than microliters. So in 1 liter, there's going to be a whole lot of microliters. So 10 to some positive exponent. Let's go to that. Volume. Examining liters now, this is 10 to the 0. This is 10 to the minus 6. What we can do, we can take the bigger value and divide by the smaller value. This will give me the difference between those 2 values every time. Now, hopefully you can see 10 to the minus 6, that's a very small number. So there's actually going to be 10 to the positive 6 microliters in 1 liter. However, mathematically, we take the big value, we divide by the small value, 10 to the minus 6, and this gives me 0 minus minus 6 is going to be 10 to the positive 6. So by doing this, it tells me there are 10 to the 6 small units in 1 big unit. There are 10 to the 6 microliters in 1 liter. Go back down here now. So 1 liter equals 10 to the 6 microliters. So I'm going to put that in right there. Again, this is telling me there's going to be a large number of small units in 1 larger unit. I then use these values to make my conversion factor. Again, anytime you can find two things that are equal, you can put them into a fraction and use that as conversion factor. Let's do the math now. Microliters cancels microliters, leaving me with liters as my units. 10 to the 6 is on the bottom. 4.6 times 10, because it's on the bottom, it comes up to the top, becomes minus 6, and my units are liters. It's in proper scientific notation, therefore, that's your final answer. So again, going back to the process here, step number 1, write down the number you're given. Find the correct conversion factor. Multiply your number by the numerator of the conversion factor and divide your number by the denominator of the conversion factor. If you set this up properly, you should have the same unit in your number as is in the denominator of your conversion factor. This will result in the canceling of those values. Lastly, write down the units that are remaining, and if necessary, convert to proper notation. Let's work through some more together. Convert 12.6 millimoles to micromoles. Notice the prefixes are the same regardless of what you have as your units here. So before we had liters, now we have moles. So the steps are, write down what you're given. 12.6 millimoles. Going to multiply by my conversion factor. I want to get rid of millimoles, so I place that on the bottom. I want to convert to micromoles, so I place that on the top. I want to find out how those two things are equal to each other. Let's go to our chart. So we're looking with moles now. So moles, we're going between milli and micro. So millimoles, 10 to the minus 3, and micromoles, 10 to the minus 6. So millimoles again, 10 to the minus 3, micromoles, 10 to the minus 6. So what you can do here is you can take the bigger number. What's number is bigger? Millimoles is bigger, micromoles is smaller. I'm going to take the big number and divide by the small number. 10 to the minus 3 over 10 to the minus 6 gives me 10 to the minus 3 minus minus 6, giving me 10 to the minus 3 plus 6, giving me 10 to the positive 3. As a result, 10 to the positive 3 is what you're looking for. 1 millimole is equal to 10 to the 3 micromoles. Work this out now. I have millimoles on the top and millimoles on the bottom. They cancel each other out. I'm left with 12.6 times 10 to the 3 micromoles. This is not in proper scientific notation. Convert that over, making that number smaller, so I have to make this number bigger. Final answer. Now, if we go back into the process here, I said there's an optional step. What we can do is we can go to the standard unit. Some students have a hard time with this right here. So an alternative way to teach this is we go to the standard unit. So here we write down what we're given, 12.6 millimoles. We're going to convert from millimoles to moles, the standard unit, and then we're going to go from moles to micromoles. Moles is bigger than millimoles, and moles is bigger than micromoles. Milli is 10 to the minus 3, so that's going to be 10 to the positive 3, and micromoles is 10 to the minus 6, 10 to the positive 6. These cancel out. These cancel out. I then get 12.6 times 10 to the 6 divided by 10 to the 3. 12.6 times 10 to the positive 3, and the rest is the same. Don't forget our units will be micromoles here. So two different methods. One method, just one jump from the unit in question to the unit I want to solve. The other one goes to the standard unit. Either way will work. Let's try example 4 together. Let's write down what we're given. 7.58 nanograms. Let's use the two-step method. We'll go from nanograms to grams, and then we'll go from grams to kilograms. Grams is bigger than nanograms. Kilograms is bigger than grams. Let's see how these two things are compared. Let's go to our chart. We have kilograms. We have nanograms. Nano is 10 to the minus 9. Kili is 10 to the 3. So hopefully you can see the difference between these is 10 to the 12, right? I'm going from minus 9 up to 3. That's a difference of 10 to the 12. If you can see that, you can do this in one big step. If you don't see that, what you can do instead is you can go from nanograms to grams, and then from grams to kilograms. You'll get the same answer. So nanograms, 9. How I remember the prefix nano, they both start with an N. 9 in nano. Kilograms, 10 to the 3. You can see we have nanograms on the top and nanograms on the bottom. We have grams on the top, we have grams on the bottom. When that is done, we're left with kilograms, what we asked for. This will give me 7.58 times, bring that up to the top, 10 to the minus 9, bring that up to the top, 10 to the minus 3 kilograms. Combine those together, 7.58 times 10 to the minus 12 kilograms. Remember what I said earlier? We're going from 10 to the minus 9 to 10 to the 3. The difference is 10 to the 12. Now, because we're going from a small value to a big value, our exponent is negative. If it was positive, if you were telling me there were 7.58 times 10 to the positive 12 kilograms in a nanogram, that's ridiculous, right? Kilograms is a big number. So ask yourself, does it make logical sense? Kilograms is big, nanograms is small. So if I have 7.58 nanograms, this should be a very small number when I convert to kilograms. What I would recommend is printing off this sheet from your notes. Use this temporarily to jump between the different values. On any assessment, I will only ask you the values that are highlighted. So make sure you commit those to memory. Please note, you cannot use this chart during any assessment. I'd like you now to do some practice problems. We have A, B, C, D, E, and F. Pause your video, give these a try. When we're done, because I think this is so important, I will take all of them up. But I'd like you to try them now on your own. Make sure you write your final answer in proper scientific notation. So pause your video, try that now. Let's take them up. How many meters are in 2.4 centimeters? So again, write down what I'm given. Multiply by my conversion factor. I'm going from centimeters to meters. Centimeters goes on the bottom so that these will cancel out. The bigger number is meters. There's going to be a whole lot of centimeters in 1 meter. Remember what centi stands for? Centi stands for 100. There are 100 centimeters, 10 to the 2 centimeters in 1 meter. When we do the math, these cancel out. Bring the 10 to the 2 to the top of the fraction. That flips the sign to a negative. And meters is our final unit. 2.4 times 10 to the minus 2 meters. Now ask yourself, does that make sense? I'm going from 2.4 centimeters to meters. Centimeters is smaller than meters. That checks out. The fact that that's a negative on your exponent is going to make this value very small. Let's try the next one now. Write down what we're given. 12.6 milligrams. I'm converting from milligrams to micrograms. Let's do this in 2 steps. We're going to go from milligrams to grams, and we'll go from grams to micrograms. Grams is bigger than milligrams, and grams is bigger than micrograms. Milli, that's 1,000. So there are 10 to the 3 milligrams in 1 gram. And micro, it's going to be 10 to the 6 micrograms in 1 gram. As a result, milligrams cancels milligrams, grams cancels grams. I'm left with micrograms as my final answer. This gives me 12.6 times, combine these together, 10 to the 6 over 10 to the 3 micrograms, giving me 12.6 times 10. I'm going to combine those together. I'm dividing two fractions with the same base, so I subtract that value. 6 minus 3 is 3 micrograms. Proper scientific notation, 1.26 times 10 to the 4 micrograms. Final answer. Alternatively, what you could have done this as one big step. We're going to go from milligrams to micrograms. Ask ourselves, which one's bigger, micro or milli? Well, milli's bigger. It's going to be a whole lot of the small units in one big unit. Let's go to our chart. What did we say? We're going from milli to micro. Milli is 10 to the 3, micro is 10 to the 6. So what's the difference between those two? The difference is 10 to the 3. So I could write that here. In the end, we work out the math. Milligrams, milligrams. We work that out. 12.6 times 10 to the 3 micrograms. Notice, these are exactly the same things. Either method works. If you can jump from where you started to where you ended in one step, that's great. Saves you some time. Otherwise, take your time and do that extra step in between. Again, it is optional. Let's try C now. 5.25 kilometers to meters. Let's do it as two steps, going from kilometers to meters, and then I'm going from meters to millimeters. Kilometers, meters, meters, millimeters. Kilometers cancels kilometers, meters cancels meters. I'm left with 5.25 times 10. 10 to the 3 times 10 to the 3 is 10 to the 6 millimeters. Final answer. Again, alternatively, 5.25 kilometers, kilometers on the bottom, millimeters on the top. Kilometers is bigger than millimeters. There's going to be a whole lot of millimeters in 1 kilometer. What's the difference? We're going from kilometers to millimeters. This is 10 to the 3. This is 10 to the minus 3. What's the difference between those two? The difference is 10 to the 6. So I could have written this in here, and you can see we get exactly the same value. Again, it doesn't matter which technique you use, just make sure you do it properly. Let's work on D. 3.45 milligrams to gigagrams. So let's go from milligrams to grams, and we'll go from grams to gigagrams. Milligrams, there are 1,000. That's what milli stands for. There are 1,000, 10 to the 3 milligrams in 1 gram. Now, gigagrams is a huge number. There's going to be a whole lot of grams in 1 gigagram. Honestly, I don't remember what it was. Let's go up and see what gigagrams is. Giga stands for 10 to the 9. So there are 10 to the 9 grams in 1 gigagram. Cancel out your units. Gigagrams is your final answer. Here we get 3.45 times, bring that up to the top, becomes minus 3. Bring the other one up to the top, becomes minus 9. Units is going to be gigagrams. Combine those together. Final answer. Milligrams is small, gigagrams is big. Therefore, you shouldn't be surprised to see a negative exponent on your value. Let's convert 9.4 hectograms into milligrams. We're going to go from hectograms to grams, and we'll go from grams to milligrams. Grams is bigger than milligrams, 10 to the 3. Hecto is actually bigger. I don't remember what hecto is. Let's go back up there. Check our chart. Hecto is 10 to the 2. So there'll be 100 grams in 1 hectogram. Those cancel out, leaving me with milligrams. This gives me 9.4 times 10 to the 2 times 10 to the 3 milligrams. Combine those together now. 9.4 times 10 to the 5 milligrams. Again, on an assessment, I'm only going to ask you those values I've highlighted. Those are values you use in the lab all the time. Things like hecto and giga in the lab, I've rarely ever used those. That's why even I'm not 100% sure of that. The good news is the internet exists, and if you had to look something up, you can. But for the ones I've highlighted, you need to know those off the top of your head. So make sure you work on that to memorize those. Let's do F now. F's a bit different. It's in scientific notation. Not a big deal. 6.3 times 10 to the 2 micrometers is what's given. I want to convert to gigameters. Get rid of micrometers by converting from micrometers to meters, and then go from meters to gigameters. Micro, remember, that's going to be 10 to the 6. And giga, we looked at that earlier, that's going to be a big number, so this is going to be 10 to the 9. Top, bottom, cancel out. Gigameters is what's left. 6.3 times 10 to the 2. Bring that 10 to the 6 from the bottom to the top. Switch the exponent to a negative sign. Do the same here with the 9 gigameters. The only difference is here now I have 3 of them to combine together. 6.3, 10 to the 2 times 10 to the minus 6 is 10 to the minus 4. And 10 to the minus 4 times 10 to the minus 9, that's minus 4 minus 9, which is going to be 10 to the minus 13. Units is going to be gigameters. Final answer. So here I've introduced the concept of conversion factors. It's how we convert one unit to another. This is the key math you need to master to be successful in a career in a laboratory environment. Notice a lot of the concepts I focused on at the beginning of this course relate to working with this. Why we spent so much time on scientific notation, on exponent laws, and a lot of time on fractions is because you need to master all of that in order to properly use conversion factor method. Without a strong understanding of fractions and moving of exponents to the top and the bottom of fractions, you would have a very hard time using conversion factor method. At your first laboratory job, your supervisor may ask you to do a calculation of how to make up a solution. If you can't do that calculation on day 1, you won't have a day 2. Make sure you fully understand all of these conversion factor methods. Here we've just done simple conversion factors. Moving forward, we'll do rate conversions, we'll do exponential conversions, we'll do non-SI conversions, and we'll do chemical conversions. That's stoichiometry. Before we get to stoichiometry, we have to review more of this. Those will be the topics of our next few lectures. That's all for today. Until next time.